next block of lectures for your second exam will begin with a discussion of enzymes. So I'd like to start out this discussion by you telling me what you know. You may have learned this in other courses in college, in high school, in other avenues, maybe at your job, whatever it might be, or watching online things. But tell me what you know about enzymes. And it's okay to be wrong, and many of you will say things that are absolutely correct. But we want to dispose of any misconceptions and reinforce those that are correct. So what is an enzyme to you?
An enzyme's a biological catalyst that's mostly made out of proteins.
It's a catalyst that lowers the energy of activation, therefore speeding up reactions.
Okay, let's take those two real quick and go through them. You said it was a biological catalyst, and you also said catalyst, which is absolutely right. It does speed up reactions. That's absolutely correct. Is it made out of protein? A lot of them are. That's true. But there are some that are not made of protein. We'll cover those as well. So it's not exclusive to proteins, although the vast majority of what we call enzymes are protein. Anything else?
Yeah, they're ribosomes. They're like ribosomal enzymes.
Okay, so some of those things, like I said, not all of them are made entirely of protein. Some are made of things like RNA, or a combination of proteins and RNA, and the ribosome is an example of that, yes. I think someone said... I'm sorry, go ahead.
Sorry, sir. Enzymes are not consumed in the reaction.
Good point. So they're not consumed in the reaction. If you can't put them on one side of the reaction substrate and product, or reactant and product, as you called it in earlier chemistry courses. You can't throw it in because it's not consumed in the reaction. So it's kind of written on the arrow. That's how we try to write it. It's involved, but it's not used up in the process. That's a good point. So we call those catalysts that aren't consumed. Good.
Without enzymes, a large amount of the processes you do in your body would not occur because it would either take too long or the reaction just wouldn't start off to begin with.
Okay, so the fact that they speed up reactions, you're saying that's half the answer, which I agree. The other half is if we didn't do that, so providing a rationale for that, then the reactions that take place in the body just either won't happen often enough or aren't energetically possible. And I totally agree. Anything else about enzymes? Or some things that they don't do, if you want to ask it a different way? I'm just trying to get an idea of what you guys already know, which is what I always do with this lecture. And if there are any misconceptions, we're going to clear them up. So it's okay to be wrong.
I may be misremembering something, but I think like one of the mechanisms is like a key and a lock that fit together for enzymes.
So I didn't quite understand it. Something about fitting together?
Sorry, maybe I'm not speaking loud enough. I said I think I remember that one of the things about enzymes is one of the mechanisms is like a key and a lock that fit together.
Okay, so one of the ways in which the enzyme binds to its substrates, we'll call them, the reactants are known as substrates for enzymes, is a lock and key mechanism. And that's absolutely true. We'll talk about that one in a few minutes. I got a slide to show you a picture of it. So that's it's not the only one, but it is one, you're right. So you guys told me a lot of things that I wanted to hear, which is great. We didn't talk on some other things because I didn't specifically ask for them. That's okay. But enzymes have things called inhibitors as well. So inhibitors slow down or prevent the action of an enzyme. We'll talk about some of those next time. And we also have some things that enzymes do not change. Like they don't change the energetics of a reaction. They don't change what we call the delta G. And we'll cover that on one of our slides later too. Okay. So let's begin. You guys know a lot of this already. I'm just going to repeat it for most of you, it appears. But let's reinforce it in case you already know it, or learn it for the first time if you've never seen it before. So you told me they're biological catalysts. They catalyze a reaction. They increase the rate of that reaction. And when we say an enzyme speeds up a reaction, be careful what you mean by that. Because we don't mean that the molecules move around faster and the chemical bonds make and break in a faster time frame or anything like that. What we mean when we say an enzyme speeds up a reaction is we really mean the enzyme allows that entire reaction process to occur more frequently, right? It takes less time between reactions and for the reaction to move on to doing it again. So when we say speed up, we really mean in terms of frequency, or how often it occurs, not how long it takes from start to finish. Okay? So when we say speed up, that's what we really refer to. It's okay to say speed up a reaction as long as you know what you mean by it. Okay? So how does it do that? Well, look at our little graph on the bottom. We're going to look at quite a few graphs today. And anytime you're presented with a graph, the first thing you should identify are the axes. So this graph is describing as the reaction proceeds, that's on the x-axis, the little blue arrow there. This is not necessarily time, because the time scales aren't consistent here. But it's as the reaction proceeds, we're going to measure the energy of molecules. Well, what do we mean by energy? Let's change that y-axis to a different word, and it can still have the same effect. So instead of writing energy over there, which is kind of ambiguous what you mean by that, let's write instability. Right? So energy here could be equated to instability, or lack of stability. So the higher on this axis, the more unstable the molecule is. Okay, so as the reaction proceeds, let's look at the let's look at the rate of the uncatalyzed reaction. So this is without the enzyme around. This is the purple trace. So without the enzyme around, we start with CO2 and water on the far left. And as the reaction proceeds, they interact with each other. And you see some interacting with each other causes it to go uphill. So there has to be an input of energy to get these two molecules to interact or to come close together. They don't want to be near each other. CO2 is nonpolar and water is a polar molecule. Yes, CO2 has polar bonds, but overall the molecule is symmetrical and nonpolar. So they don't want to interact with each other too well. Okay? And even if these two were in solution or as a gas, they don't interact that well. And so we go over that hump, so there's a high point in that hump, and eventually we get to the other side and it goes all the way downhill to making the H2CO3, which is carbonic acid. Okay, so water and CO2 can react with one another to form carbonic acid. And as you notice on the right-hand side of that graph, the trace has become much lower than it was when we started. Right? So where we started over here in the instability or energy axis was at this point, and we end up at this point. So we're at a lower position. That means the overall energy of the reaction has decreased. So you had to lose it to somewhere. So it was released to the environment. Right? We call this an exergonic reaction. So the total energy of the reaction has released some energy to the rest of the universe. Okay? So how do we describe how much energy was released? We're going to call that the delta G of the reaction, and we'll talk about this a little more later. But how do you measure the change of any value? You always measure the final value minus the initial value. Right? So if I asked you, how old are you? You take the year you were born and the current year, and you subtracted current minus the year you were born, and it gives you a positive number. That's how old you are, right? You don't subtract it the other way around and get a negative age. So the same thing here. We're going to take the final energy, which is this value here, right, or instability, minus the original, and since the original was larger, this change is negative. So this has an overall negative delta G. Anybody, does that sound familiar to any of you? Does that ring a bell? What do you know about overall negative delta Gs?
Means the reaction is spontaneous.
Exactly. So we're going to call those spontaneous reactions. That means they happen without any major input of energy, right? It prefers to go in that direction. Let's just call it that. Will it do it on its own with nothing else around? If I put CO2 and water in a jar, and will they leave it sitting on a shelf for a few million years? Will it come out as all carbonic acid? Maybe. Depends if I can get over this hump or not, right? That's going to require some energy. Now, if I put that jar in normal atmospheric pressure and temperature, then yeah, it'll probably do this over time, but very slowly. And by slowly, I mean infrequently, right? We're going to use it in that terms. But if I put this in a jar of CO2 and water, at a much lower temperature, say, in a deep freezer somewhere, this reaction is going to occur at a much slower pace because it doesn't provide the energy to get over this hump as often. Okay? Of course, if I heat the jar up, it occurs more rapid. Okay? So how does an enzyme affect that? So let's look at the rate with the enzyme. As instead of going over this huge purple hump, we're only going to go over the green one. So what did the enzyme do? We often say it lowers this energy of activation, right? That amount of energy you have to put in to get this thing started. Okay? And that's one possible way an enzyme could do this. It's not the only possible way. It's a very common way to do it. But it lowers this activation energy. But what did it not change? Okay, it's very important to realize that the activation energy went down, but these endpoints where the CO2 and water were this unstable, and now this thing is at a certain energy level or a certain instability, those endpoints did not change by adding the enzyme. Okay, they don't change the energies of the resultant molecules or the beginning molecules. All it does is change the path you take from one end to the other. So it's like finding a shortcut to your destination. Well, I don't have to go around this long bend. I just have to go over this small one. So the amount of energy you have to put into the system to get it over that hump has been reduced in the presence of the enzyme. And like she said, the enzyme is not consumed in this process, so once it's done, it can go back and do this over and over and over until it eventually falls apart. Because most RNAs and proteins eventually fall apart. They're not permanent. Okay? The other figure on the slide indicates how these enzymes, whether they're protein or RNA, can distinguish between chiral molecules. Right? So this molecule on the right with its 4 colorful shapes around it, this carbon with its 4 single bonds, is a chiral molecule. So there's a D or an L or an R or S or E or Z conformation to it, whatever these might be. And the one below it is the other enantiomer. Right? It's the other conformation. So if this was R, this is S. If this was L, this is D, and so forth. But this surface represents the enzyme and how it interacts with this potential substrate. So you can see the one at the top, these 3 atoms match perfectly with the shapes below them. So the enzyme would recognize this. Whereas the one below it, there is a mismatch. And there's no way you can rotate this thing to make the 3 pieces match down here. The only way to make the bottom one match is to change it into its other enantiomer at the top. So the enzymes can distinguish chiral centers. Right? And it's very important for doing a lot of the chemistry we're going to talk about. Okay, so some other definitions we need to go through so we can understand what I mean when I say something, and so we can talk to each other using these terms. So we already said it's a catalyst. It speeds up, and by speeds up, again, we mean more frequent. The reaction doesn't speed up the rate of the chemical step, but it does speed up how often this reaction takes place. So how much faster does it take place? So how many times per second more often, if you want to think of it that way. So it goes from, say, 10 to the third, 1,000 times faster, which is kind of on the sad end for enzymes. That seems a lot. Like if you can type at a certain rate, and then I give you a enzyme, and now you can type 1,000 times faster, that seems rather impressive. But for enzymes, that's not very impressive. But on the high end, it could be as far as 10 to the 17th times faster. And that's not 17 times faster. That's a 1 with 17 zeros after it. So that's 100 million billion times faster than it was before. It's a huge improvement. Right? Not all of them are that fast, of course, or that much improved, but many of them are somewhere between the two. Right? So we call the reactants for enzymes substrates. So I'll refer to a substrate all the time, and of course the product is still called a product or products if there's more than one. We already said they're stereospecific. And they're also reaction specific. So this is unlike you did in organic chemistry, where in organic you had a reaction that took place like a Markovnikov addition or something like that, where you had an asymmetrical molecule added to an asymmetrical double bond. You probably remember that one, right? Like adding water to a propene or something, right? Well, one side's going to get the H and one side gets the OH, and I'm sure you remember all that with Markovnikov's rules. And the major product was to follow the rule and put the hydrogen on the less substituted side and the OH on the more substituted side. And then you had this small chance of it making the minor product, right, where it doesn't follow the rule. And so most of your chemical reactions were like that in general chemistry and in organic chemistry. And then you had to purify your wanted product from the small amount of alternative products, alternative reactions, and so forth. Well, in enzymes, the enzymes make 100% the same product all the time. There's no alternative products, right? They can tell chiral centers apart. They don't make side reactions. They do the exact same reaction and make the same products 100% of the time. Okay, so it seems a little difficult coming from an organic point of view, where how does it prevent the side reaction? Well, the enzyme has an active site, as you see down there, called its little pocket, where amino acids have folded up into a certain shape, and they accept the substrate or substrates and do the reaction very specifically. Right? It only does the same reaction, and it only does it the same way every time. Okay, so unlike our more ambiguous result from a chemical reaction, this one's very, very specific. It always gets the same product. It always looks for the same substrate. That's not to say that some enzymes may use more than one substrate, and that's entirely possible. But one substrate will never generate a variety of products. It'll always be the same product. All right, let's look at an example of one of those. At the top here is our friend CO2 and water again, just like we showed on the first one. And on the right will be the representation of carbonic acid. Okay? And of course, carbonic acid is a carboxylic acid, would have a pKa somewhere in the low range of 2 to 4, something like that. And it would deprotonate and become bicarbonate. Right? So this is what happens in your blood. Your tissues are producing CO2 as a byproduct of metabolism. We'll cover that when we get to our third and fourth blocks. And that CO2 is not very soluble in water. Remember, it's got some polar bonds, but overall it's non-polar. So to make it more soluble in water, you don't need your blood looking like a carbonated soda, right? So to make it more soluble in water, we're going to add water to it. And now the carbonic acid on the right is soluble in water, very. Okay, so why do this? We're going to transport CO2 around in the blood in a soluble form rather than in a gas. So when your carbonic acid passes by the lungs and you need to expel the CO2, you need to do so as CO2, as a gas. So we need to convert it back to CO2. So this brings up another point, that enzymes are generally reversible. Right? Some enzymes are totally irreversible, but most are reversible. Sorry about that, it is raining outside. I don't know if you can hear the thunder. So when we take our CO2 and water and turn it into carbonic acid, or we take the carbonic acid and turn it back into CO2 and water, we need to do so rather quickly, because it doesn't spend that much time passing through the alveolar cells of the lungs. And so if you look at this chart, we have a few enzymes listed here. At the very bottom is carbonic anhydrase. That's our enzyme we're talking about. And if you look at the uncatalyzed rate, right, it says 1.3 times 10 to the minus 1 per second. So that's basically saying we do one reaction every 7 to 8 seconds. Right? It's very slow, or very infrequent. But the catalyzed rate in the presence of this enzyme does about 1 million per second. That's quite an improvement, right? So we go from doing one every 7 or 8 seconds, far less than 1 per second, and we end up with doing it 1 million per second. So this is a huge rate enhancement, which the rate enhancement over here is in the order of like 8 million. But for enzymes, that's a decent number. It's not that great. There are faster ones. So one of the fastest or the largest rate enhancements is the OMP decarboxylase, which we'll talk about later when we get to metabolism. And if you look at its catalyzed rate, it looks rather meager compared to this 1 million down here. It's only 39 per second, right? That's very slow compared to carbonic anhydrase. So you think this is a very poor enzyme. However, think about what it's accomplished. In the absence of this enzyme, OMP decarboxylase, the rate of this decarboxylation reaction is about 2.8 times 10 to the minus 16 per second. Or, put it in terms of how long it takes to do one, roughly 113 million years is how long it takes to do one reaction. So this is a ridiculously slow reaction in the absence of the enzyme. So in the presence of the enzyme, achieving 39 per second from a starting point of basically not happening is quite an accomplishment, right? Even though it's not terribly fast compared to this one, the rate enhancement is much, much better. Okay, so don't think OMP decarboxylase is a poor enzyme. It might be going slower than carbonic anhydrase, but overall it's achieved a much greater rate enhancement than the reaction occurs in its absence. Okay? And we've got lots of examples in between. Okay? So let's look at some examples of enzymes and their specificity. Okay? So one example are called proteolytic enzymes. So these are peptidases, right? And they hydrolyze a bond in a protein. Okay? And we just went over proteins and their synthesis. So if you look at the top, there's an example of a peptide chain there. And shown is one peptide bond. Okay, it's between the amino acids R1 and R2 in the chain, whatever they might be. There's many others there. We just labeled them 1 and 2. And this enzyme, in the presence of some small molecule, doesn't have to be water. In this particular enzyme, we're going to use water. But we're going to break this bond. We're going to break this peptide bond. We're going to hydrolyze the bond. Okay? Hydrolysis doesn't imply the use of water. It means some small molecule has come in to break a bond. In the case of water, when you break this bond, just like when you added water to the asymmetric double bond, one side's going to get an H, one side's going to get an OH. So what happens here is the water breaks the bond, and the nitrogen gets an H, and the carbon gets an OH, and it becomes a carboxyl group. And of course it would deprotonate right away in the pKa in the solution, so it'd be a carboxyl group, right? On the other side, your amino group would immediately gain another proton because of its pKa, so forth, and would become the protonated version of the amino group. Right? So I've split the two apart. We have a carboxyl group and an amino group resulting from an amide bond. And that's what they were when we started, when we were building the peptide. So it just simply breaks the bond. Okay? So if I look at a protein or any peptide chain, and I add one of these proteolytic enzymes, you're thinking perhaps it cuts every single peptide bond. Well, they're more specific than that. They only cut peptide bonds, that's true, but they're very specific about which ones they cut. So, for example, if you have a lysine or an arginine amino acids, R group sitting here, and then you want to cleave the bond immediately after that, right? Then I have a very specific enzyme that can do that, right? In this case, trypsin only cuts on the carboxy side or the ending side after one of these basic residues. Okay? So if I have a lysine or an arginine, then it'll cut this bond. And that's what trypsin does. It won't cut it unless it's one of these basic amino acids. Thrombin is even more specific. It'll only cut the bond if it's an arginine followed by a glycine. Right? And there are other sequence consequences as well, or sequence requirements as well, but mainly it's an arginine followed by a glycine. Now, why would you want to be so specific? So these two enzymes aren't just floating around anywhere in your body, right? And I don't want them cleaving all the proteins they run into, because they would just turn you into a puddle of goo, right? They'd break every single bond we spent all this work making. So we only want to control when they cut things. So we only allow it access to the substrate when we'd like it to happen. A lot of our digestive enzymes are like that. We only keep them in our stomach and small intestine. They're not allowed to go everywhere. Right? So they only digest the food, not you. Right? And thrombin is used in blood clotting. It triggers a cascade of other events that coagulate the blood. If that were to run rampant in the blood, you turn into one big blood clot, and that's not very conducive to circulating oxygen. Right, so we'd like thrombin to be only used if it encounters this particular region and some other triggering factors that make it work. Okay, so we have to be very selective about it. Okay. Some other parts of the enzyme I want you to know is not all enzymes are just protein, right? And I don't mean the ones that are RNA as well. I'm talking about something else. So even for the RNA enzymes, they're not just made of that one thing, right? Let's use a protein as an example. So I have a protein sitting here, and I know it's an enzyme. Perhaps it's one of these digestive enzymes. But the protein part alone, when I assembled it at the ribosome, when it folded up, doesn't work. It needs more parts. It doesn't have all its parts yet. Much like we did with the RNA polymerase, it had all those subunits, right? The alpha subunits and the beta prime and so forth. This one has to acquire something that is not made of protein. Right? We call that a cofactor. Okay? Cofactors are part of an enzyme that is not made of the enzyme itself. Right? You think of it as a copilot. Okay? So a cofactor is a small thing, usually a metal ion or a small organic molecule, not its substrate, but some other molecule, that it binds in order to help it do its job or allow it to do the chemistry. As shown here is an example in the picture that this particular enzyme has acquired a zinc ion, right? Without which it will not be able to do the chemistry. So how does it hold on to this zinc? There's a couple histidines and a glutamate here that are forming coordination spheres for this zinc. Okay, so that's often how you hold metals. Okay, so here we have a little hierarchy again, like we did with structures or levels of structure in protein. A cofactor is any part that was added after the protein was assembled. So it's a copilot. It's another piece it's picked up, but it's not made of protein. Some of them are metals, right? Some of them are not. Some are small organic molecules. If it's a small organic molecule, and we'll discuss a few of these in a second, then it's still a cofactor. It's still a copilot to this enzyme, but we also give it the name coenzyme. Okay? Whereas metal ions, we just give them the designation, I guess, cofactor. They are not coenzymes. So if you think of it in terms of, let's say, fish, if cofactors are fish, right, then some of these cofactors are, these fish are sharks. They're organic molecules, but not all organisms qualify to be that, right? You can have lots of organic molecules out there that are not coenzymes. But all sharks are still fish. They're still called cofactors. Okay? And there's plenty of other fish out there that are not sharks, right? Those would be your metal ions. They're still cofactors, but they're not coenzymes. So if you think of it, coenzyme is a subset of the cofactors, those that are not metals, basically. Okay, so here's a list of all those things. Not every one of them out there, but a lot of them. We have some cofactors on the left and the enzymes to which they belong on the right. Some of the cofactors listed on the left are just metals, as you see, and the others are called coenzymes. All of these are still cofactors. Okay, do I want you to memorize this? No. But realize these are parts of functional enzymes. They need them to work. A lot of these you may recognize. You see coenzyme A, we see biotin, we see flavins, we see thiamines, we see nicotinamides. So what do you think we get a lot of these coenzymes? What should stand out in this chart to you?
A lot of them are vitamins.
Exactly. A lot of them are vitamins, in particular your B vitamins. So, and others, but a lot of these are vitamins. And a lot of the metals we also acquire in our diet, right? We don't eat the metallic metal, but we get these ions from eating other organisms and other things and foods. But all these are required to make these enzymes work. Okay, so when we drink things like, I see students all the time with their energy drinks full of B vitamins, they're supplying you with a lot of these coenzymes that your enzymes need to function. Okay? Of course, those drinks supply far in excess of what you need, but they are supplying those molecules that you can't make on your own, right? That's why they're called vitamins. You must acquire them in your diet. Now, bacteria and some yeast and other organisms can just make all these themselves. They don't need energy drinks. They don't need to eat any of the stuff. Okay, so back to some numbers real quick. We hinted at this early on, and I talked about the difference between the energy of the products and the reactants, or the substrates and the products. And we called it the delta G. And you correctly told me that if the difference, products minus substrates, was negative, then it was spontaneous. And that's entirely correct. Okay? Adding an enzyme did not change those endpoints. So enzymes do not change delta G. I think I'm going to say that 50 times over the next few weeks with you guys, but I'm going to ask it 50 different ways. Enzymes do not change the delta G, or the free energy of the reaction. Another way to ask it, just one more of many I'm going to ask, is adding an enzyme, can it change the spontaneity of a reaction? No. It does not change the reaction because it does not change delta G. Delta G is either positive or negative, whatever it is for that reaction. Adding the enzyme will not change it. So what's the point of the enzyme? What did it do? Oh, I remember from the chart, it lowered that activation hump, right? It lowered that path to get to those products. So it does change the amount of energy required to get it started, or the activation energy. It's often written EA, or E with a double dagger, or just the double dagger itself to indicate the transition state. Okay, so enzymes will change the activation energy. It's one thing they can do, but they will never change delta G. Okay, so if I ask you about a reaction, you can tell me two things. You can tell me if it's spontaneous, and you get that information from the sign of the delta G, negative or positive. And then I can ask you, how fast or how frequent is this reaction? It could be very fast or very frequent reaction, or it could be a very infrequent reaction. It doesn't occur very often. Does the delta G determine how often it occurs? No, not at all. But the activation energy does. If that's a very large hump it has to get across, like our one for OMP decarboxylase, it's a mountain it has to climb over, right? Without the enzyme, it's hardly ever going to go across that mountain, right? So you get one reaction that might occur every 100 million years. But in the presence of the enzyme, that mountain of activation energy is now a small bump, right? And so it can occur more frequently. And we said 39 times per second, which is greatly enhanced. But neither of those have a difference in delta G. It's the same delta G both cases. Okay? So an enzyme can speed up a reaction, but it will not change its spontaneity. Okay? I can ask that in many different ways. Okay, so let's look at these standard conditions of a reaction. We need some basis from which to measure them. So the actual delta G is what happens in the real world. Right? If I look at an enzyme in a cell or in a test tube or under a microscope or whatever it's doing, can't see the enzyme itself, but I can see the effects. It's converting substrate to product at a certain rate, and it's doing it with a certain amount of input of activation energy, and so forth. That's the actual state, right? So that's real world conditions. What we're going to call standard state is our human-defined reference point. That's all it is. So we're going to call it standard temperature. That's your room temperature, right? Your 298 Kelvin or 25 Celsius. Standard pressure, at sea level at the Earth. That's our standard because that's where we grew up. Right? We're going to call it 1 atmosphere of pressure. Standard solute concentrations. Everything's 1 molar, right? 1 mole per liter. And then we have this R constant to make the units work out for our chosen units. Well, under standard state conditions or standard conditions, that's great for a lot of chemical reactions. We do 25 Celsius, we do 1 atmosphere, and everything's 1 molar, and see what it does. Try that in a cell, and nothing will work. Nothing is 1 molar in a cell. That's a ridiculously high concentration. And to put that in perspective, what if the proton concentration was 1 molar? Well, that's 1 times 10 to the 0, right? 1 is 1 times 10 to the 0 molar, and that would be a pH of 0. And that's quite acidic, and that's not how cells operate. So we have a pH of roughly 7 to 7.4, and we call that the standard biological state. So instead of calling it delta G naught, the little 0 superscript represents naught, or standard state, we're going to call it delta G naught prime. We'll add another superscript on the superscript. So it's just like the standard state, except it's our biological state, where the only thing we change is let's not do things at pH 0, we're going to do them at pH 7. Right, which is more in line with the way a cell would work. But again, this is not even close to reality because nothing's going to be 1 molar, right? So we call the standard state as a reference point to calculate a number, and then we compare it to the actual state, right, of delta G, which is under real world conditions where the concentrations are not 1 molar. Okay? So a couple other graphs I want to show you, and I'll explain them to you. So again, we'll look at the graph at the top right. First thing we should identify are the axes. So this is describing over time, this is time now, as time progresses, how much product is present. Well, if a reaction's going in the forward direction, turning substrates or reactants into products, the amount of product should increase over time. Right? It should accumulate. And that's what this graph is showing. In the absence of any enzyme, that will slowly accumulate over time. It's not going to be very fast or very frequently making product, right? But over time, it will accumulate a lot of product. And if you go hours, and in some cases, hundreds of centuries, right, later, it eventually will make a lot of product. We don't know how long this will take, but eventually it'll get there. Right? But in the presence of an enzyme, what's changed? Well, early on, in the first few seconds to minutes or so, the amount of product has gone up very rapidly. And then if we wait long enough, it's essentially the same as it was without the enzyme present, right? So it looks like this curve in the red case here, or even the black one if we let it go long enough, they look like they reach a point where it levels off, right? It looks like it's approaching an asymptote, right? What do you think that asymptote represents? If I could draw a horizontal line up here where these lines will eventually read if we wait an infinite amount of time, what do you call that amount of product?
Max product?
What's that?
Maximum product?
Okay, maximum product, it's not wrong, but let's think about what that means. It's the maximum amount of product I could achieve under these conditions.
That you've maxed out your reactants?
So will there be more or fewer reactants available at that point than when we started?
Fewer.
Fewer. Will this reaction still be ongoing?
Yes.
Yes, and we're going to assume that this is your standard enzyme where the reaction is reversible. It can go in both directions. And it's choosing to go in the direction that's favored, right? Whichever one's spontaneous and whichever one has the lower amount of reactants product side, right? That's Le Chatelier's principle. So eventually, what will happen? If I start with a reaction in a system and let it go long enough, what will it do?
Reach equilibrium.
It will reach equilibrium, right? So that's a good word. What does the word equilibrium mean here?
Equal concentrations of a concentration of products and reactants where you're forming the same amount of products as the reverse reaction.
Okay, so careful how you said it, which you're not wrong. The amount of substrates and products or reactants and products aren't necessarily the same, but the rate of each of their formations is the same. So the forward reaction rate is equal to the reverse reaction rate. Their concentrations could be wildly different, right? It's not necessarily the same. But the formation of each and the destruction of each by the enzymatic process is the same in both directions. So we reached equilibrium. Okay? When we started, we were not at equilibrium. Clearly, we had all substrates and no products. And so the enzyme is getting us closer to equilibrium. Right? But the enzyme gets us closer to that dotted horizontal asymptote up here. Gets us really close rather rapidly. Right? Whereas here, it was approaching it very, very slowly. But if you wait long enough, they will both reach equilibrium. The difference is the enzyme gets us closer to it sooner, right? But adding the enzyme, did it change the equilibrium point? But follow these two curves. If I add enzyme, no enzyme, or add enzyme, does it change the point at which I end up in the end?
Slightly.
Remember, we have to keep going forever to reach equilibrium. Where that's that dotted horizontal asymptote I'm drawing up here. It's imaginary, but it's there. They will eventually reach the same point. So adding an enzyme doesn't change the equilibrium, which is another way of saying it does not change the delta G. Okay, so they do reach the same point eventually. It might take a very long time for some reactions in the absence of an enzyme. But what the enzyme does is get you much closer to that point far sooner. Okay, that's all we really care about. We never want to reach equilibrium. Equilibrium is a death sentence for a cell. We always want to stay outside of equilibrium so that there is an energy source available. Okay? So let's look at another graph over here. This is the one I showed you earlier. It's the reaction progress, not necessarily time, but as the reaction proceeds. And here's our free energy again, or instability one more time. So here's where our substrate starts, and here's where our product ends. So our delta G for this reaction would be the number here on the y-axis minus this larger number for the substrate, and that's going to be negative. So this reaction is spontaneous because it ends up lower than it started. Okay? But what is this point at the very top of the curve? Right? So we sometimes call it the double dagger. It's an indication for transition state. But it's the point at which the molecule is least stable. Right? It's the highest point on this y-axis. And remember, our y-axis was instability. So this is the point where it's very unstable. If you pushed it up this hill, it would love to fall down either side. It's not going to go any higher, of course. But you have to get it over this point, beyond this point, so it forms product. What the enzyme does is lower the requirements to get to the top of the hump. Okay, so in order to start at this substrate's energy and end up at this hump, I have to go this high. That's the delta G double dagger. I don't like using that term because it confuses you. It's not delta G for the reaction, so we're going to call it the activation energy. Right? So this difference is called activation energy, and for the absence of the enzyme, it's fairly large. But in the presence of the enzyme, it's much smaller. But the presence of the enzyme did not change our starting and ending points. So it did not change the delta G, and thus does not change the equilibrium point. Okay, so let's look at how this thing actually works. So here's an example of an enzyme. This is lysozyme. It's a very common enzyme. And if we were actually in lab, you would crystallize this. It's very easy to crystallize. You actually do it every day. Just don't realize it. You're all protein crystallographers in some way. You just never look at your results. So lysozyme is found in almost every secretion on your body. And its goal is to kill bacteria. Right? So it punches holes or prevents the repairing of holes that it makes in the bacterial cell wall. So you make this, and over time it tends to crystallize very, very easily. So when you wake up in the morning and you've got that hard, crusty thing in the corner of your eye, that's mostly dead cells and bacterial debris and a lot of salt, but some of it is crystallized lysozyme as well, right, which killed those bacteria. So this is a useful enzyme. Let's see how it works. The bacteria are going to disagree. They're going to be the ones that don't like the video, right? But the enzyme here folds up. You notice on the bottom it says part B. You have all these amino acids lined up, 129 of them. This is representative of the primary structure, right? And then it folds up, and A represents the tertiary structure. You see there are some alpha helices and some loops and turns and a very small beta sheet in there. But some of these amino acids, the colored ones here, the numbered ones, end up next to each other in three-dimensional space. They are nowhere near each other in sequence, but when you fold up, they all end up in this little pocket. Okay? So these are the ones that form what we term active site, and that's where the substrate binds. Okay? We're going to talk about inhibitors later and some misconceptions of what active site means there, but an active site simply means where the activity takes place. It's active, right? This is where the chemistry of the enzymatic reaction takes place. So it's a place where the substrate binds. Right? Most substrates do not bind covalently. They bind with many non-covalent interactions. These could be hydrogen bonding, could be non-polar interactions, could be ionic bonds, could be pi stacking, lots of other things, but it's rare that it's a covalent bond. We do have some bonds that way, but most of them are a variety or many weak interactions. Okay? So that's termed our active site. This is where the reaction takes place. But the first step of any reaction, of any enzymatic reaction, is the enzyme must bind its substrate or substrates. Right? So let's talk about one for now. The enzyme must physically grab its substrate. Right? It must bind to each other, touched. There's no action at a distance. Right? It doesn't send the substrate a text and say turn it into product. It doesn't work. Okay, so it must bind to it. So how can it bind to it? And this is what you were talking about early on. So in the late 19th century, Emil Fischer came up with the idea that the substrate fits the enzyme like a lock and key. The enzyme being the lock and the substrate being the key that fits in it. And you see the little diagram here. The active site is a mirror image, or not a mirror image, but I guess like a glove that fits the substrate, right? It's a perfect fit. And that very well explained the idea that an enzyme is very specific for a certain substrate, and certain substrates are very specific for only so many enzymes. So the idea made sense. It's a lock that fits in a key that fits in a lock. Okay? And then in the mid-20th century, Daniel Koshland came along and said, wait a minute, that doesn't fit this enzyme I'm studying. Because the enzyme I'm studying, it happened to be called hexokinase at the time, right? Can use lots of different sugars as its substrate. It doesn't just use glucose. It prefers glucose, but it'll use fructose, it'll use mannose, it'll use any other 6-carbon sugar, so we named it hexokinase. Right? So how does the lock and key explain that promiscuity of using different substrates. Well, it can't. It says this is a lock, there's one key for it. You can't have more than one key fit the lock. So he came up with the idea called induced fit, where the enzyme's active site isn't so rigid, it isn't so unmoving, right? It's more amorphous. And then the substrate binds and induces it to take on the substrate shape. Now, not any substrate will do, but some substrates will cause the enzyme to adopt the shape that fits the substrate when it binds. And that explained how certain enzymes, like hexokinase and several others, fit so many substrates, but not any substrate. So who was right? Was it the lock and keys correct, or is induced fit correct? Because they both seem to describe some enzymes perfectly. Well, in fact, they're both right. Many enzymes work exactly like Fisher described, a lock and a key. And quite a few enzymes work purely like induced fit. Some have a little bit of both. So if you can imagine an enzyme where the part that says A there is definitely fixed in place, it doesn't move at all, it's very rigid. The part that says B and C might be able to move around and fit another part of the substrate. So it's still selective on which substrates it will accept, but one group on that substrate, perhaps one not amino acid, but maybe a carboxyl group, could be a little longer or shorter, or it could have an extra methyl group on it. So it's a little adaptive to one part of the substrate, but one part is rigid. It must be this. So in fact, they're both right. It's a combination of these two. Some enzymes are exclusively lock and key. Some are more like the induced fit variety. Most of them are somewhere in between. Okay, so here's our example of hexokinase that he was describing. So what this enzyme does, and we'll cover this when we get to our metabolism section, but it takes glucose and ATP, that's its two substrates, and it transfers a phosphate from the ATP. It has 3 of them, so it takes the last one and puts it on the glucose. And the leftover piece is ADP, a diphosphate, and the glucose with a phosphate attached on its number 6 carbon. It's very simple. It just transfers a phosphate. Okay, so how does it do this? Well, first thing the hexokinase does is binds one of the substrates. Right? There's 2 substrates. It's very unlikely they both show up at the exact same time. So it binds one of them, and that's shown on the right in the little picture. So when A is showing it in its open conformation, it's not yet bound, and then that little molecule binds, and then it changes. You can see it's like a little crab claw. It pinces onto that molecule and gets the closed conformation. When it's in the closed conformation, the other substrate can now bind. So the first substrate to bind here is actually ATP, and when it changes shape, it actually forms a pocket that fits glucose or any other hexose sugar. So the ATP binds very rigidly, right? It fits perfectly in there. It won't use anything else. But when it adopts its new shape upon binding the ATP, there's a pocket for glucose now, and the glucose goes in and it's induced to fit the glucose. Right? So this is how this works. So a lock and key could not explain this behavior. Okay, let's move on to transition states. This is that high point in the curve, right, where the activation energy was provided, and we're at the top of the curve, right? On the on the y-axis again, we called it energy, but we could also call it instability. Okay, so the transition state, the very top of the curve, is the least stable arrangement of the substrate. Okay, so this is very distorted or strained molecules, right? They don't like this positioning. Okay, so if you're going to twist this molecule to form its product, you better hold on to it tightly because it doesn't like this. Okay, so when the enzyme binds its substrate, and we compare that affinity, remember we talked about a molecule fitting or not fitting. If it doesn't fit very well, it has a very low affinity, and if it fits in the site very well, it has a high affinity, right? If we compare the substrate's affinity to the enzyme compared to the transition state's affinity for the enzyme, it's 10 to the 10th or 10 to the 15th times more tightly bound as the transition state. So it binds those transition states exceedingly tightly. But they're very, very unstable. They don't stay there. If the transition state were very stable and it bound this tightly, it essentially would bind the molecule and never let it go. Right? That wouldn't be a very useful enzyme. That would be a great way to bind something and just never let it go. And there are situations that happens, like avidin binding to biotin is like that. It binds very, very tightly, tighter than this, and just never lets it go. So here, we're binding our substrate not very tightly, but better than the wrong molecule, and then we coax it into its transition state. We're going to need some input of energy to do that. And when you get to the transition state, we will never let it go as the transition state. It's bound very tightly. And of course, it won't stay there. It'll go over the hump or go back to being substrate, and then it won't be bound so tightly. And I have an example of that at the bottom. We can take advantage of this tightly binding transition state to come up with drugs. Okay, so the enzyme I'm talking about here is an enzyme that converts L-proline to D-proline. Okay, so it's just an isomerase, right? It's a prolyl isomerase. It takes proline in its L form, which you see on the left there. It's a normal looking form of proline you find. And we're going to turn it into D-proline. So we're basically making an isomer. But the only thing we're doing is changing the geometry around that alpha carbon. Right? So here's our carbon, here's our alpha carbon with its amino group, and then the R group of proline has this loop. Right? So if you do the math here on the shape of this is the L or levo conformation. And when I'm done, it's exactly the opposite, and now it's in the dextro or D conformation. How do we go from here to here? Well, if you remember from chirality, we talked about this at the beginning as well, and we did this back in organic, that you can't rotate a molecule into its other enantiomer. It's impossible. That's why they're not the same molecules. In order to turn one molecule into its enantiomer, you must switch any two of the things bound. Or another way to say that is remove one of them and reattach it on the other side. And that's exactly what we're going to do. So you can imagine this proline here. The geometry about the central carbon has what shape? Right, so the L-proline on the left, the alpha carbon has what geometry?
Tetrahedral.
It's tetrahedral, right? It's 4 single bonds. And then when I get to D-proline on the product side, it's still tetrahedral, right? But the proton, the H here, is, imagine being it behind the board in the beginning. Now it's coming out at you, right, on the D-proline. So what happens is the enzyme will pluck off this hydrogen because it's the only one that's easily removed here, right? So we'll remove the proton, right? That leaves what on the carbon if I deprotonate it? What will be on this carbon now? Think back to organic. Just losing the proton.
A lone pair.
It'll be a lone pair, exactly, a lone pair of electrons. And a carbon with 3 single bonds and a lone pair of electrons, we term a carbanion, right? It's a negatively charged carbon ion, right? And again, with the lone pair, if I just pluck off the hydrogen, leave the lone pair there, it'll still look tetrahedral because that lone pair still is one of our Vesper groups, so it takes up space. But I need that lone pair to be on the other side. I need to push it to the other side so I can put the proton back on, and I'll make D-proline. But can you imagine in the process of this tetrahedral arrangement becoming the other tetrahedral arrangement, that lone pair, it's not a real atom, right? It's just a pair of electrons, and they're delocalized. So I can shift it from one side to the other, right? But along the way, won't the other 3 atoms at some very unstable point in the center be planar? Where the lone pair is moving from one side to the other, at that very moment where it moves from one side to the other, it's very fleeting, right? The 3 other atoms will be planar. That's going to be a very strained, unstable, it doesn't like that conformation. That's the idea behind transition states. So L-proline going to D-proline has a very short-lived, fleeting moment where that carbon is going to be trigonal planar. So we design a drug that mimics that because we know this enzyme holds on to its planar transition state very tightly. So let's design a drug with a planar carbon here. It's easy to do, just put a double bond in it. All right, so this carbon over here on the right in this drug is perfectly planar, right? Because it has a double bond. And this is a very stable molecule, right? It's exceedingly stable, right? Whereas this one, where it's a planar transition state with a lone pair switching from, it's very unstable. Okay? So if I give this drug to prolyl isomerase, it will bind it so tightly that essentially looks like a covalent bond. It's not covalently bound, but it binds it so tightly because it resembles the transition state that it'll never let it go. And that's a great inhibitor of this enzyme because it's going to spend all its time bound to this drug rather than binding substrates and products and releasing products. Okay, so a lot of our drugs that inhibit enzymes are transition state analogs. They're mimics of the transition state where they take the thing that makes it unstable, eliminate it, and then make it so that you can't use this molecule as a substrate. So this can't be used because it's very stable. If you were to draw this on a graph, remember this part here was where we start, this is our product where we end, and this was our hump over the middle, transition state. This one won't be a hump to get over, it'll be a pit it falls into because it's more stable than L-proline and D-proline bound there. Right? It prefers to bind it much more tightly. So instead of being a hump to get across, it's a pit it falls into. It's a deep pit, and it can't get out of it. And I have an example of that with this I guess a sort of analogy of explaining how enzymes work. It's called a made-up enzyme called stickase. And this enzyme breaks sticks. And it happens to break metal sticks. So I guess we could have called it something else, but stickase works. So what this thing does is in the absence of any enzyme, we have a metal stick sitting here, and at some point we end up with a bent metal stick, and then it breaks in two. The chance of this happening in the absence of the enzyme is very, very, very low. Right? Metal sticks don't spontaneously bend and break. Right, so this is a great example of an enzyme a fictional enzyme, that would have a reaction in its absence that rarely occurs, ever. Okay? And if you graph that on the right, we have our substrate, our product, and this hump is huge, right? The energy needed to break the stick will rarely come from the outside world, right? You're not going to get enough energy to get over this hump, so the stick rarely ever breaks. So it has a negative delta G, yes, it went down, but just because it's spontaneous doesn't mean it's going to happen. It has a very low frequency of occurrence because this I don't want to call it delta star, this activation energy is very large. Okay. Let's add our stickase enzyme. Let's first make the enzyme look like this. We'll make an enzyme that's lined with magnets, so it binds to our stick, and nothing happens because it binds to our substrate very, very well. It's perfectly designed to bind to the stick. And so what happens is the enzyme, our stickase enzyme, binds to the stick through the magnets. It makes an ES complex, E being the enzyme, S being the substrate or our stick. So an ES complex, and this is very stable because it matches it perfectly. In our diagram over here, we have our substrate, the enzyme comes along and binds to it, and it falls into this huge pit, which is very, very stable. Remember, instability on the y-axis. So if I go down, very stable. And it just sits here forever. Nothing ever happens. This is a very poor enzyme. A better idea is to make the enzyme shape mimic the transition state, the bent stick. So we design it such that the magnets look like the bent stick, not bent, the very unstable part, right before it breaks. Here, the stick doesn't bind very well to the enzyme initially, but as the stick starts to bend, it fits the enzyme better and better and better until it finally fits perfectly. But it's at the very point where either the stick wants to go back straight or will break. Right? It's the least stable orientation of the stick. But the enzyme mimics that perfectly, so it stabilizes that transition state. In our graph over here, we don't have to go over this huge hump anymore. We just have bending of the stick. We might have a few humps in here. The path might look complicated, whatever it is, but it never has to input a large amount of energy, only this small amount. And we end up at the same product, a broken stick. So the delta G is the same, but the ease of getting here was a lot safer road. It's easier. You don't have to climb this mountain anymore. Whereas if you design your enzyme like this, now to make the stick bend, not only do you have to provide this energy to bend the stick, you got to bend the enzyme. So this is a huge activation energy, all the way up this blue line. So this is not going to break. Okay, so this is an example of how enzymes generally have a shape that mimics the transition state, not the substrate or the product. Okay, so here's a practice question for you. So which of these statements is false? Let's go through the 5 statements and see true or false. So A says enzymes form complexes with their substrates. True or false?
True.
True. They have to bind to them, exactly. There's no sending it a text and say, do your thing. All right. B says enzymes often lower the activation energy for chemical reactions.
True.
True. Without the enzyme, it would just be a chemical reaction. And with the presence of the enzyme, it lowered that activation energy for that reaction. That's true. All right. C. Enzymes change the equilibrium constant for chemical reactions, the KEQ.
False.
False. Exactly. And enzymes do not change the equilibrium constant. And if you remember from the general chemistry, the Nernst equation down there, that delta G is the standard delta G naught plus some indication of the amount of substrates and products around. That's what that RT, natural log of Q, means. Q is basically the ratio of products to substrates. So if you change the ratio of products to substrates, you're either adding more product, taking away product, adding more substrate, or taking away substrate. Adding an enzyme does none of those things. Right? Adding the enzyme changes the activation energy. We know it does not change delta G, so it can't change anything in that equation. Okay, good. D says many enzymes change shape slightly when the substrate binds. True or false?
True.
True. Which ones are those?
The induced fit model.
Yes, that's the ones that adopt at least part of itself, maybe all of it, to the induced fit model, right? Good. And then E says the reactions occur at an active site of enzymes, which is a precise 3D arrangement of amino acids, an important feature of catalysis. True or false?
True.
That's true. That's the definition of our active site. It's those amino acids that have come together not necessarily in the primary sequence, but in three-dimensional space to make a pocket for the substrate. Okay, good. Here's another example of an enzyme. It's called catalase at the top. And basically it takes peroxide, hydrogen peroxide, and degrades it into water and O2. And if you balance the equation, it takes two peroxides, which is not shown in the figure, but two peroxides together and reacts them and makes two water molecules and releases a molecule of O2 as a gas. Right? That's all the enzyme does. So it kind of limits the danger. It removes peroxide from solution. Right? Although it has an awful name. It's the worst named enzyme in the history of named enzymes. So I guess this one was named at like 4:58 p.m. on a Friday before a 3-day weekend. They're looking at the sub thing. What is this molecule? What's this enzyme doing? It's degrading peroxide into water and O2. I don't have time to name that. It's catalyzing something, right? Let's call it catalase. Let's go home. That's a terrible name, right? It's just a name that it got stuck with. Peroxidase would be a much better name, but it's stuck with the name catalase. Okay, so let's talk about how enzymes are named, because that's a poor example of naming an enzyme. Let's come up with some better rules for naming it. Some enzymes were discovered and researched decades and even centuries before we came up with this scheme of naming enzymes. And those names have kind of been grandfathered in, right? We stuck with those. And that's things like pepsin and trypsin, right? So those names are not going anywhere because they've been studied for a very long time. To give you an idea how long those digestive enzymes like pepsin have been studied, back before you were allowed to do experiments on other people and animals and everything else, and it was considered not something you should be studying anyway. This was talking thousands of years ago. People would study this. They take a piece of meat, and they knew you had to digest it somehow, right? So where does that take place? It has to take place inside your body. So they would take a piece of meat, tie a piece of string around it, swallow it, right? Wait a few minutes to an hour or so, and pull it back up, fish it out of your stomach, right? I'm sure it wasn't pleasant. But pull it back up and notice that the meat had been partially digested. And they could figure out what was happening to it by the smell, by the color, again, they tasted it afterwards again. So you could do all the experiments you wanted on yourself. You didn't have to have permission. So that's how they discovered a lot of these digestive enzymes before we had this convention of naming enzymes. So how do we do it today? Generally, enzymes end in the suffix ase. So if you see an ase ending, it's probably an enzyme. Right? But saying ase is not enough. There's plenty of other things I need to include. So how about some information about what this enzyme does, right? So what kind of enzyme, what kind of reaction does it catalyze? That would be important. What else would we like to know? I'd like to know what are its substrate or substrates. Okay, so for example here we have sucrase. Sucrase is an enzyme that clearly works on sucrose. What does it do to sucrose? I really don't know from the name. It's not the best name, but there's really not much you can do with sucrose other than degrade it into its components of glucose and fructose. So we kind of realize that sucrase represents degrading or pulling apart or decomposing that disaccharide into its two monosaccharide parts. Okay. Another example are oxidases. They catalyze oxidation to tell you the reaction they catalyze, but it kind of left out the substrate. So these two names, sucrase and an oxidase, give me half the part I want, half the name I want. I'd like to know what your substrate or substrates are, what reaction you're catalyzing, and then I'll append that with an "ase" suffix. And then I know everything I need to know. So let's look at a better example. Okay? So if we have something that gives us the name of the substrate, the type of reaction it's performing, and then throw "ase" on the end of it, I can tell you exactly what it does. Okay? So we'll look at many examples of those later. The ones I just mentioned were just shy of doing that, but we did name one earlier. We had carbonic anhydrase. Remember the one that took our CO2 and water and made carbonic acid? Well, in fact, it's describing the reverse reaction. Carbonic anhydrase is taking the carbonic acid and breaking it into CO2 and water. It's a totally reversible reaction. But the name carbonic anhydrase sounds like it's taking carbonic acid and doing an anhydrase reaction to it. That sounds like I'm removing water. That's exactly what it's doing. I'm taking carbonic acid and removing water, and whatever's left I release. It happens to be CO2. Okay, so from the enzyme's point of view, it's removing the water from the molecule and leaving CO2 behind. Okay? And that's carbonic anhydrase is telling me what it's doing. Okay, so it's a great name for the enzyme. Okay, so the last thing I want to do for today's lecture is go over the classification of enzymes. There's many ways to go about classifying enzymes. We're going to go with the standard classification of 6 main classes. There is a newly formed, or not necessarily, it's not a new enzyme, but it's a new class of enzymes. It's the 7th class that may or may not get promoted to a real class or not. It's still under discussion. So we're going to stick with our 6 historically main classes of enzymes. And I want you to be able to tell these apart. The chart on the right lists a lot of subclasses for these to give you ideas of what they do, but I don't want you to memorize those. What I want you to know is the 6 main classes and how to tell them apart based on the chemistry. Okay, so we're going to run down these 6 classes, and I'll do some examples of each. Some are easy and some are more difficult. So oxidoreductase should be easy to visualize. It's an enzyme that does a redox reaction, an oxidation-reduction reaction. And it's by far the most abundant of these categories, right? There are more enzymes in class 1 here than any other. So there's plenty of redox reactions. Okay? If you're not a redox enzyme, then we'll consider putting you into one of the other classes. So the next class here is called a transferase, not necessarily the next most abundant, but just got number 2 in the list. And these are enzymes that take a molecule from one atom, take a piece of one molecule away from a substrate and give it to another molecule. So they have to take it from a substrate and give it to another substrate to make the products. That's what transferases do. The thing they take away and give to the next molecule must be bigger than a proton. Because if they're just transferring a proton or transferring electrons, we're back to oxidoreductase again. Okay, so transferases transfer things bigger than hydrogen. Like you could have a methyl transferase, or a transferase that transfers phosphates, or that transfers entire sugar molecules. So whatever it is, as long as it's bigger than a hydrogen. Okay? Class 3 are called hydrolases, and hydrolases break single bonds. Okay, they take a single bond and turn it into no bond. Right? So that's what a hydrolase does. It may use water to do that. We talked about one earlier with our peptide bond breaking enzymes, right? Peptidases. But it doesn't have to use water. Water is the most common way to do it, but it doesn't have to use water. It could use ammonia, it could use phosphate, lots of other small molecules. But if you have a single bond, right, a sigma bond, right, remember those, and you break it, and the only thing left is two pieces, then you had a hydrolase. Okay. Let's skip number 4 real quick because it's kind of the enzyme class of last resort. It's the most difficult to understand. So, in my opinion. So let's go to number 5. These are isomerases, much easier to understand. They simply make an isomer. We start with one molecule, and we do some chemistry to it, and we arrive at an isomer of that molecule. We may have removed some pieces and added some things back, but in the end, it has the same formula. So we probably rearranged some of the atoms. We made an isomer. But it's overall the same molecular weight, it has the same parts, it's just now attached differently. Okay? So that's the isomerase. Number 6 is a ligase, and it does ligation, or ligatures, right? It puts two things together. It takes one molecule and attaches it to another molecule. The most common of these is making new carbon-carbon bonds, which are difficult, right? But it's not the only thing you can do. It just takes two things and puts them together. Those are ligases. This is exactly the opposite of hydrolases. And that leaves us with lyases. So it sounds like ligase, but it's a lyase. And what lyases do is, unlike all the rest, they must, in the simplest terms, accomplish two things. They must make or break a double bond. So either you go from a single bond to a double bond, or a double bond to a single bond, but without doing any redox, right? Because if you do any kind of redox or oxidation reduction, you're back in category 1 or class 1 oxidoreductase again. And that's true no matter what. If you do any redox, you're in class 1, no matter what else you're doing. But if you're not doing redox and you happen to make or break a double bond, then you're a lyase. Okay, and I'll explain the differences in those as we do some examples. Okay, so let's look at the first one and do an example. So class 1, and I don't care if you know their numbers, class 1, 4, 5, 3, 2, 6, whatever, but know their class names. All right, so an oxidoreductase does this kind of chemistry. So if you notice at the top, it takes two substrates. One is in its reduced form, and it becomes oxidized. The other is in its oxidized form, and it becomes reduced. You can never do a redox or oxidoreductase reaction without doing both of those things. You can't oxidize something unless you reduce something else. If you remember from organic, our definition for oxidizing something is to remove its electrons. Right? So if I'm going to take this molecule A and oxidize it, I'm removing some electrons. I have to give them to someone. They can't just be released as electrons. Right? And the enzyme can't retain them forever because it's not consumed in the process. So I have to give them to someone else. So this thing that's being reduced is the acceptor of those electrons. Right? That's reducing a molecule. Okay, so in the example here, we're going to use the enzyme alcohol dehydrogenase. And if you're taking the lab, we're going to use this enzyme in lab. And what it does is it takes this alcohol, it's your favorite alcohol on the left, ethanol. Right? I'm going to oxidize it. Since it's a primary alcohol, it's going to oxidize to an aldehyde. And those electrons I'm taking from it, I'm going to give to NAD+, which is another molecule we'll learn the structure of later. But it's going to accept those electrons and become a reduced version called NADH. Okay, so what I'm giving it is 2 electrons and 1 proton. That's why it's extra protons sitting out here. I took 2 electrons and 2 protons from this guy and gave them to this one with 1 left over that doesn't get attached. Okay, so this alcohol is now oxidized to an aldehyde, and NAD+ has been reduced to NADH. This is a redox reaction. It's totally reversible. I can take the product here, the aldehyde, and reduce it back to an alcohol, right, by giving it some electrons that I take from this molecule. Right? NADH could be oxidized to its NAD+ form because I extract some electrons, giving them to the aldehyde to make the alcohol. So it's redox in both directions. And unless told otherwise, most enzymes are generally fully reversible. Okay, so that's oxidoreductase as an example. There are many others. That's just the one I used as an example. Below it is our transferase. We're going to take, in this case, one molecule A and one molecule BC. Well, part of BC, whatever part might be, in this case the B part of this molecule, BC, is taken from C, or from BC, leaving C behind, and given to A to make this molecule called AB. Okay, so a part of the latter molecule was taken from it, leaving part of itself behind, and given to the first molecule to make this new molecule. Okay, this is not a ligase. I didn't take two individual things and just glue them together. I took it from someone, gave it to someone else. So the example here is I have fructose 6-phosphate, for example, just a sugar with the phosphate on it already. And ATP is going to donate a phosphate. Okay, ATP gives up one of its phosphates, leaving a DP behind. And that phosphate is attached to this fructose to make it a doubly phosphorylated fructose now. So this molecule donated a phosphate to this molecule. And the enzyme facilitates that transfer, right? So the enzyme is the middleman, right? It's transferring the phosphate from one molecule to another. So this is a transfer. Okay. The third one, hydrolase. We've seen this example already. We have a peptide chain, for instance, right? We're going to break this bond. So in the molecule generic example, I have an AB molecule, right? And I'm going to break the bond between A and B. In this example, I'm using water. It doesn't have to use water. And when I break the bond, I'm breaking a single bond or a sigma bond. One side gets H, one side gets OH, right? And the two are now separate. I could have used ammonia for this, and one side would get H and one side would get the amino group. I could use phosphate, one side would get H and one side would get the remainder of the phosphate. Any small molecule will do. Water is the most common example used, but it's not the only way to do it. So don't associate water with hydrolase. I'm warning you on that one. It's not the only thing that uses water, and hydrolases don't necessarily have to use water. So don't make that association. But what you can make is, I have a single bond, and that bond has been broken. Right? No redox involved here, so it's not an oxidoreductase, it's a hydrolase. Break a single bond. That's what they do. Okay. The liases, I said, were very difficult. I'm briefly going to skip it and come back, just like I did on the other list. So let's move on to 5 and 6 real quick, and I'll go back to number 4. Why is it he using that one as the last one? Because it's technically number 4 in the list of enzymes, so I'm going to keep that consistent. But let's do 5 and 6 first. And they're easier to understand. So here's isomerase is 5. I take A and turn it into B. A and B have the same formula, right? Otherwise it wouldn't be an isomer. So an example of that is taking this molecule here with its 3 carbons and 3 oxygens and a phosphate. It's a ketone at the moment, and I'm turning it into an aldehyde. I'm moving the double bond onto the first carbon. Now it's an aldehyde with its 3 oxygens and a phosphate. So same formula, I've just moved some bonds around. In fact, I moved a hydrogen around to accommodate. So I didn't do any redox because the molecule was at the same oxidation state. There was only one molecule involved. I've moved some double bonds around, and I moved a hydrogen around. Okay, so it's an isomerase. A and B have the same formula. I didn't add or remove anything net, and I didn't do any redox. I didn't break any single bonds that weren't, pi bonds other than hydrogen. So it's just an isomerase. All right, the last one on the list here, number 6, is a ligase, and it simply takes A and B and makes AB. This is usually a difficult reaction, so we have to put some energy into it in the form of hydrolyzing the ATP. So ATP becomes ADP and phosphate. However, you notice neither of these end up attached to the AB. Right? I'm not attaching them to anything. I'm not transferring that phosphate. I'm just using the breaking of this bond to power the assembly of this bond. Right? So this carbon-carbon bond here is formed at the expense of breaking the ATP's bonds. So I'm making this new carbon-carbon bond. Okay, so this is a ligase. Right, and lastly, look back at number 4. In this example, this is a lyase. I'm taking this double bond, turning it into a single bond, or this single bond into a double bond at the expense of adding a small molecule. It looks a lot like a hydrolase so far, but I'm not breaking a single bond. Taking a double to a single or single to double at the expense of some small molecule, and I'm not doing redox. That's important here. So you must not be doing redox. We'll go over briefly at the beginning of next lecture how to tell if you're doing a lyase or a redox reaction. It's a very simple counting method to do this, and I'll use this example. Okay, so after this classification of 6 things, I want you to consider what would happen if you run any of these in reverse. Would it be the same enzyme? Would it be the same class? You decide. Some of them are, some of them are not. Okay? And so here's a summary of those things to put all those words into very short-term things. Oxidoreductases clearly do oxidation reduction. That one's fairly easy. Transferases transfer groups. They take it from someone and give it to someone else. Hydrolases break sigma bonds, right? They break a single bond. And then when they're done, there is not a bond. Okay? Ligases do something a little different. They use small molecules to turn a double into a single or a single into a double without doing redox. Isomerases simply rearrange, make new bonds, but they have the same formula before and after. It's an isomer. And ligases use some sort of other reaction, like breaking of an ATP molecule, to put molecules together. Usually there's an input of energy required, so like making new carbon-nitrogen or carbon-carbon bonds. Okay? And I have a little analogy for these for you that covers 4 of the 6, and the other 2 aren't really involved in the analogy. So let's talk about how we do transferases, hydrolases, isomerases, and ligases with this analogy. Now, oxidoreductase and lyase, I'm saving for next time. I told you I have a little counting method to tell those 2 apart. But the other 4, transferase, hydrolase, isomerase, and ligase, I can use a pair of dry erase markers to explain these. So if you have a pair of dry erase markers, grab them. Okay, make sure they have caps. So take 2 dry erase markers with their caps on. I want you to take the cap off of one of them and put it on the back of the other one. Right? Assuming you have the type where the cap can be put on the back. Right? So take the cap away from one and attach it to the other one. That would be a transferase. I took a piece of one molecule and gave it to another, and your products are now a marker without its cap and a marker with 2 caps on it. Right? That would be a transferase. Okay? Set one of the reset it, put your marker cap back on where it belongs. So you have 2 regular markers again with their caps. And I want you to set one down. You only need one for this next reaction. We're going to take that marker and take its cap off. You don't give it to anyone. You just take the cap off and let the 2 things go. That would be a hydrolase, right? Because you broke a single bond. You took the cap off of the marker. That's all you did. Okay? That's a hydrolase. Okay, put your marker back together. Let's start with one marker again this time. You're going to take the cap off and put it on the back of the marker as if you're ready to use it. Okay? That would be an isomerase. Right? So you take the cap off, but you reattached it not in the same way. When you're done, you still have all the same parts. It has the same molecular formula, right? The marker plus cap, right? But it is an isomer of how it started. The cap is not on the same place. It's a different molecule now. So that would be an isomerase. Okay? Now I want you to begin with your marker laid on the table without its cap on. So the marker is sitting on your table and the cap sitting on your table, and no one's touching them. They're just sitting there. You pick both of them up and put the cap back on the marker and let it go. That's your reaction. So the reaction of picking up the writing part of the marker and the cap laying there, putting them together, that would be a ligase. So in essence, a ligase looks like the reverse of a hydrolase. Okay? And they often are. Not always, though. Okay? I can't use this analogy for an oxidoreductase because it's hard to visualize oxidation reduction with this method. And of course, your bonds here you're breaking, it's hard to tell if they're single or double bonds. We're going to assume they're all single for this analogy. But next time I will tell you how to tell oxidoreductases from ligases. Or if you want to preview, look at the very first video ever uploaded on here. There's a little dog holding a flower in his mouth. I think it's a flower. And the first 13 minutes of that video is exactly that definition of how to tell an oxidoreductase from a ligase that I did for another class. Okay? There's a practice question here at the bottom that can help you do that. Go through those, make sure they make sense to you, and you can tell these 6 apart. Here's some more practice questions. There's 6 more listed here. You can go through them slowly and tell which one is which. Some of them are a little tricky, like the last one here. Make sure you can tell which one is which class.